Cosmology, the study of the universe as a whole, has been turned on its head by a stunning discovery: that the universe is flying apart in all directions at an ever-increasing rate. Is the universe bursting at the seams, or is nature somehow fooling us? The scientists whose data revealed this accelerating universe have been awarded the Nobel Prize for Physics. And yet, since 1998, when the discovery was first announced, scientists have struggled to come to grips with a mysterious presence that now appears to control the future of the cosmos. Dark energy. On remote mountaintops around the world, major astronomical centers hum along with state-of-the-art digital sensors, computers, air conditioning, infrastructure, and motors to turn the giant telescopes. Deep in Chile's Atacama Desert, the Paranal Observatory is an astronomical mecca. This facility draws 2 megawatts of power, enough for around 2,000 homes. What astronomers get for all this is photons, tiny massless particles of light. They stream in from across time and space, by the trillions from nearby sources, down to 1 or 2 per second from objects at the edge of the visible universe. In this age of precision astronomy, observers have been studying the properties of these particles to find clues to how stars live and die, how galaxies form, how black holes grow. But for all we've learned, we are finding out just how much still eludes our grasp, how short our efforts to understand the workings of the universe still fall. Cosmology, the study of the universe as a whole, goes back to the ancient Greeks. With no telescopes or other optical instruments to probe the stars, observers constructed models designed to make sense of what they saw. Their earliest theories stated that all matter in the universe is composed of some combination of 4 elements: earth, water, fire, and air. Each arises from opposing properties of heat and cold, dry and wet, acting upon more primitive forms of matter. Aristotle took it a step further. He held that the universe is divided into 2 parts: the realm of earth, in which everything is composed of the 4 substances, and the realm of the stars and planets. These bodies are made up of a 5th substance, unchanging and incorruptible, called ether or quintessence. The Greek idea that the universe is a series of concentric circles with Earth at the center yielded to a wealth of new discoveries about the universe. That Earth is a planet. In a solar system, located in a giant wheel of stars and gas, a galaxy. Bound by gravity to a local group of 30 galaxies. Bound in turn to a cluster of over 1,000 galaxies. And to a supercluster with tens of thousands of galaxies. This, our cosmic region, takes up a volume about 100 million light-years across, set within a larger pattern of galaxy filaments, superclusters, and enormous empty voids. Earth is but a speck within a firmament so vast we can scarcely imagine it. For all we've learned from snatching photons, the most basic nature of the universe has only grown more mysterious. Ironically, modern models have recalled the mysterious fifth element conjured by the Greeks to explain a universe that appears to move in ways not easily explained. To understand the predicament now faced by scientists, let's see how they got there in the first place. 100 years ago, most astronomers believed the universe consisted of a grand disk of stars and gas, the Milky Way. They saw stars like our own sun moving around it amid giant regions of dust and luminous gas. The overall size and shape of this island universe appeared static and unchanging. That view posed a challenge to Albert Einstein, who sought to explore the role that gravity, a dynamic force, plays in the universe as a whole. There is a now legendary story in which Einstein tried to show why the gravity of all the stars and gas out there didn't simply cause the universe to collapse into a heap. He reasoned that there must be some repulsive force that countered gravity and held the universe up. He called this force the cosmological constant, represented in his equations by the Greek letter lambda. It's often referred to as a fudge factor. In 1916, the idea seemed reasonable. The Dutch physicist Willem de Sitter solved Einstein's equations with a cosmological constant, lending support to the idea of a static universe. Now enter the American astronomer Vesto Slipher. Working at the Lowell Observatory in Arizona, he examined a series of fuzzy patches in the sky called spiral nebulae, what we know as galaxies. He found that their light was slightly shifted in color. It's similar to the way a siren distorts as an ambulance races past us. If an object is moving toward Earth, the wavelength of its light is compressed, making it bluer. If it's moving away, the light gets stretched out, making it redder. 12 of the 15 nebulae that Slipher examined were redshifted, a sign they are racing away from us. Edwin Hubble, a young astronomer, went in for a closer look. Using the giant new Hooker telescope at the Mount Wilson Observatory in Southern California, he scoured the nebulae for a type of pulsating star called a Cepheid. The rate at which their light rises and falls is an indicator of their intrinsic brightness. By measuring their apparent brightness, Hubble could calculate the distance to their host galaxies. Combining distances with redshifts, he found that the farther away these spirals are, the faster they are moving away from us. This relationship, called the Hubble constant, showed that the universe is not static, but expanding. Einstein acknowledged the breakthrough and admitted that his famous fudge factor was the greatest blunder of his career. The discovery revolutionized astronomy because it redefined the universe as a dynamic realm. But if he were around today, Einstein would be surprised to see his own failed idea return. If the universe is expanding, it must have emerged from a dense and hot primordial state. A cosmic fireball, we now call the Big Bang, would have supplied the initial kick. Even as the universe expanded, gravity began drawing matter together into a web-like structure that gave rise to galaxies and stars. If there's enough matter out there, will gravity one day rein in the Big Bang and cause the universe to collapse in on itself? To find out, astronomers renewed Hubble's quest to precisely measure the cosmic expansion rate. Working with the Hubble Space Telescope and giant new observatories on land, they sought to measure distances far deeper than Hubble ever could.
People are talking about doing precision cosmology for the first time, because it used to be cosmology, well, we have a rough idea how big the universe is, maybe to a factor of 2 or 3, but now with these new measurements, we're really getting a handle on the overall density and structure of the universe. And what they're telling us is not what we expected to hear.
Hubble's mileage markers were the Cepheids. Today, astronomers look for stars like our Sun in their death throes. They spend their lives gradually consuming the hydrogen gas that makes up their cores. At the end of the line, the dying star swells and sheds its outer layers, leaving behind a tiny dense sphere the size of Earth. It's so dense that if you could scoop out a teaspoonful of matter from its core, it would weigh 1,000 metric tons. If this white dwarf happens to orbit another dying star, it may begin to draw upon the companion's expanding outer layers. At a critical threshold, it can grow no more, and it explodes. Scientists at the University of Chicago and Argonne National Lab have been simulating the thermonuclear reaction that begins deep within the star. A nuclear flame sends hot ash rising to the surface. It breaks out, then begins to wrap around the star. A collision on the other side of the star triggers the explosion. Because Type 1a supernovae are all thought to explode in the same way, and because they are extremely bright, they are ideal for measuring extreme distances. It's like looking at cars with identical headlights approaching on a highway. The dimmer they appear, the farther away they are. By documenting explosions through the depth of the universe, 2 groups of astronomers had hoped to find out how quickly gravity has been reining in the cosmos. Capturing the trickle of photons from events 6 or 8 billion years ago would test the sensitivity of even the most powerful modern telescopes. When they spotted a Type 1a supernova, astronomers looked at how much its light was shifted to the red. The larger the shift, the more the universe had expanded since the explosion. They combined this measurement with its distance, based on the apparent brightness of the supernovae. Some explosions looked dimmer than expected based on their red shift. That meant their light had traveled over a greater distance to reach us. That led the 2 teams to the same conclusion, that the cosmic expansion rate had been slower in the deep past. For the universe to reach its current size, the expansion had to actually accelerate. Scientists have known since the 1930s that the universe is not necessarily the way it appears. Back then, astronomer Fritz Zwicky measured the rotation rate of spiral galaxies and found that their gravitational pull was over 100 times greater than what he expected, based on the amount of matter he could see. There must be some gravitational presence, Zwicky surmised, that you can't see with a telescope. He dubbed it dark matter. Scientists today have successfully recreated the structure of the universe in computer simulations by incorporating dark matter in the gravitational sources that sculpted galaxy clusters and filaments. Apparently, we now find out there's another unseen presence at work in the universe, called dark energy, and it's whisper thin. For comparison's sake, water has a density of 1 gram per cubic centimeter. Dark energy is a mere 10 to the minus 29th grams per cubic centimeter. That's a point, followed by 28 zeros and a 1. The equivalent of 5 hydrogen atoms in a cubic meter. In their scan of the early universe using the WMAP satellite, scientists concluded that matter and dark matter account for only about 26% of the content of the universe. The remainder, then, is dark energy.
Since 1998, something totally unexpected happened, which is we discovered that not only our universe is expanding, this expansion is accelerating. This is a classical who ordered that type situation. In 70% or so is dark energy in the universe. About 70% of the surface of the Earth is covered with water. Imagine we didn't have a clue what water was. This is the situation we're in.
So what exactly is it? The simplest answer takes us back to Einstein and his repulsive force, the cosmological constant. It's the idea that empty space is actually a seething stew of particles popping in and out of existence. It's a type of energy that is constantly welling up from the vacuum. This description is reminiscent of the sudden and violent outpouring of energy that many scientists believe launched our universe in the first place. Long after the Big Bang, vacuum energy exerted enough pressure over extremely large scales to push the universe out. And as the universe grew larger, more and more of it came into existence, causing the expansion to accelerate. Another explanation takes its name from Aristotle's quintessence. While similar to vacuum energy, in theory it can vary over time. There are still other theories. One unifies dark energy and dark matter into a single dark fluid that alters the action of gravity on large scales. Another digs deep into a warren of hidden physics to suggest that the push of dark energy may one day turn to a pull. This theory predicts that in about 10 billion years, the universe will begin cascading back together in a big crunch destined to reduce all of creation to the size of a proton. Is there a way out of all this cosmic confusion? Some scientists suggest that the findings derived from Type 1a supernovae might be based on an illusion. that the measurements are due not to cosmic acceleration, but to large-scale factors we have not yet detected. Since Nicholas Copernicus showed that the Earth rotates around the Sun, cosmologists have based their theories on the idea that we exist in no special place. In that case, our view of the universe is similar to any other vantage point in the universe. That assumption has allowed us to extrapolate what we see to a vast scale. We concluded, for example, that the universe has expanded in a uniform manner. That explains the uniform temperature of light from the early universe, within which we can see a pattern of variations. And it explains the uniform distribution of galaxies, within which we see a pattern of filaments and clusters. Is it possible that we are still only seeing part of a much grander cosmic map? It's like looking at a desert and assuming the rest of the world is flat, when in fact it's filled with oceans and mountain ranges. Perhaps there are non-uniform cosmic structures larger than our field of view, forming bulges or bubbles. For argument's sake, if we are located in the center of a giant bubble, then supernovae out on the fringes might seem to be accelerating away. Or if we are in a region of higher density, the universe might appear headed for collapse. For now, it looks like the discovery of the accelerating universe is holding up. Scientists using NASA's Galaxy Evolution Explorer telescope confirmed the finding by using galaxies in the distant universe as another kind of mileage marker. As another check, they calculated the speed that galaxies should collapse into clusters based on their collective gravity. The data showed that something is holding them back and breaking their fall into the clusters. The discovery of dark energy is a major accomplishment in this age of precision cosmology. Ironically, its effects may well be lost on our distant descendants. Right now, we're in the outer suburbs of a great cosmic metropolis, the Virgo supercluster. In time, gravity will drag the Milky Way and the rest of the local group into the city limits, then stir us into the giant melting pot of a mega-galaxy. By then, if the wider universe is accelerating outward, we'll see little evidence of where it all came from. Distant galaxies visible today will begin to pass beyond our vision at speeds exceeding that of light. Those distant generations will know less about the nature of time and space than we do today. For now, as the data trickles in one photon at a time, our minds struggle to unravel the mysteries of a dark universe as they race ever faster beyond our dim horizons. air conditioning, infrastructure, and motors to turn the giant telescopes. Deep in Chile's Atacama Desert, the Paranal Observatory is an astronomical mecca. This facility draws 2 megawatts of power, enough for around 2,000 homes. Cosmos. Dark energy. On remote mountaintops around the world, major astronomical centers hum along. With state-of-the-art digital sensors, computers. What astronomers get for all this is photons, tiny massless particles of light. They stream in from across time and space, by the trillions from nearby sources, down to 1 or 2 per second from objects at the edge of the visible universe. In this age of precision astronomy, observers have been studying the properties of these particles to find clues to how Is the universe bursting at the seams? Or is nature somehow fooling us? The scientists whose data revealed this accelerating universe have been awarded the Nobel Prize for Physics. And yet, since 1998, when the discovery was first announced, scientists have struggled to come to grips with the mysterious presence that now appears to control the future of the Cosmology, the study of the universe as a whole, has been turned on its head by a stunning discovery. That the universe is flying apart in all directions at an ever-increasing rate.